For this lab, you will be studying electron configuration, but before we go into depth of what electron configuration is, I thought I'd give a brief lecture about the subject as sort of background information. So first, electron configuration, simply in its most simplest sense, is the distribution of electrons for a particular element. Now for hydrogen, that's going to be easy because hydrogen just has one electron in its orbital. But for other elements across the periodic table, you'll have multiple electrons, and those electrons are going to be housed in different orbitals, at different energy levels, so to speak. So before we actually get in depth into electron configuration, there's a couple of things that are worth noting. Number one is that an electron is not just a wave, and it's not just a particle. So in this case, an electron has both of these properties of a wave, in which case it will have a wavelength and an amplitude and energy associated with that as the wave propagates in one direction. And an electron is not only just a particle, that in which case it's just housed in what are known as these orbitals. Some of these orbitals are closer to the nucleus housing the protons and neutrons, and some of these electrons are housed sort of far away from the nucleus and can easily just get removed and get ejected from the atom. So these electrons that are housed sort of far away from the nucleus in orbitals that are at a great distance from the nucleus, we call them valence electrons, while those electrons that are housed sort of inner proximity and closer to the nucleus are so-called core electrons. So the core electrons actually shield the valence electrons. So thinking about an electron as a particle or thinking about an electron as a wave, you have to reconcile both of these two behaviors. So before we actually talk about electron configuration, you have to realize that the electron has these two properties: property of a particle that's housed in these energy levels known as orbitals, a property of a wave, which means it's actually traveling through space with an energy at a corresponding frequency, wavelength, and amplitude. So in this particular case, thinking about electrons housed in these orbitals, they're energy levels that have a great distance or a closer distance to the nucleus, as which we said before contains the protons and the neutrons. Protons are positively charged, neutrons are neutral in charge. But if you take a look at a substance such as lithium, you have two electrons in this shell, and that shell is full, but you have a third electron here. Now, if that third electron actually leaves, this lithium ion, because remember ions are the gain or release of an electron, so if lithium actually removes that, what we call valence electron, it actually has an electron configuration that is isoelectric with helium. So by lithium kicking off this electron, it has an electron configuration. The two electrons are the same configuration as helium. It's nearest noble gas. So when we think about electron configuration, we actually can determine why some elements like to be +1 ions or +2 ions or -1 ions or -2 ions, simply because they can actually attain their nearest noble gas configuration. Now, this has to deal with ionization energy. That is a term where you provide enough energy to kick the electron out of the atom, so it's completely ejected out. In most situations, the energy that you provide to the atom are not enough to kick it out. But what it can do is excite it, and it excites that electron to a promoted state. And when it gets promoted within the atom, when it gets promoted, it actually likes to go back to the ground state. We call it going back to the ground state relaxation. So when it goes back to the ground state, it actually emits energy. You can actually see that here in a series of emission spectra. So if you energize an electron to the +7 energy level and it relaxes back to the +4 energy level 4, then you have an emission of energy called a bracket series. So some of this emission as a result of relaxation happens in different regions of the electromagnetic spectrum. It could happen in the UV region, it could happen in the infrared region, and in some cases it could happen in the visible region, in which case you can actually see the colors that are emitted. So when you do not have enough ionization energy, but you have enough energy to excite it to another energy level, promote it to another energy level, Then what happens is that electron actually relaxes back from excitation to what is known as the ground state. That also results in the emission of energy in some form in the electromagnetic spectrum. But you want to contrast that with just simply ejecting the electron out of the nucleus. All of these require quanta, which means a discrete energy level. And so you cannot just add any energy and expect the electron to get ejected. It has to be a specific amount of that energy, nothing more, nothing less. We call that energy packets as a quanta. So just as a reminder, this is the electromagnetic spectrum. Some cases when you excite an electron from a ground state to a higher energy level within the atom, it's going to relax and it will emit. So usually we find emission in the visible region, the UV region, in some cases the infrared region. Many elements have emission spectrum, and some elements such as sodium or hydrogen can actually emit if you excite it with specific quanta and emit visible energy so you can see it. It will come off as either a red color, orange color, yellow color, blue color, etc. So all of these waves have a wavelength that increases. But as you increase the wavelength, you notice here you're actually decreasing the frequency. The product of wavelength and frequency in the electromagnetic spectrum always equals the speed of light. So you may have heard of wavelength times frequency with their inverse proportion. Their product will always equal to the speed of light 3 times 10 to the 6th meters per second. So coming back to this quanta, a quanta simply means that it's a specific discrete energy packet. So as an example, if I have a particular particle that I want to excite to a higher energy level, I can't just use any willy-nilly energy. I have to be very discrete. So the analogy is like a staircase. You can put enough energy to have this electron go from this level down to this level. But you cannot have 1 foot here and 1 foot here on the staircase. It's a very specific quanta of energy to get it down this staircase. Similarly, in the green, it takes a very specific amount of energy to get this down all the way to this step. You may think, oh, I'll add a lot more energy, and with that more energy, I could get down to the ground. Not so. If you have more energy, you not be able to get to the ground. If you add a little bit of energy, you won't be able to get to the ground. You have just the right amount of energy, not more, not less, hence a quanta of energy gets it to the ground. Notice here we're talking about an electron in this particular cartoon as a particle, but you have to be able to reconcile the notion that an electron can be as a particle or it can be as a wave. So this has to do specifically with quanta. So that quanta is a discrete energy level. Usually it's the product of Planck's constant times the frequency. The higher the frequency, the more energy is involved in that electromagnetic radiation. So let's come back to electron configuration, which is what you'll be studying in this lab. I liken electron configuration to an address, or sort of the location of an electron that you're going to house within the atom itself. Remember, the atom is your nucleus and all those orbitals that surround the nucleus. So here's an address. This is my address, 241 Post Oak Drive, the apartment, city, and zip code. So if I were to parse this address and pick the 4 most elements to define that location of where I am in time and space, I would define it as the road number, that's one part of my address, the city, the state, and the zip code. So all those 4 things together, road number, the city, the state, and the zip code, define my location in time and space. Similarly, you're going to do that with an electron when you plot electron configuration. That one electron is going to be defined by 4 items. And those 4 items are known as quantum numbers. So think of an electron configuration as one electron determining its address. The address of the electron is 4 things that determine it, or 4 quantum numbers. Just like there's 4 things that determine the address where my location will be pinpointed. You're going to have 4 quantum numbers, because we're talking about quantum mechanics here, 4 quantum numbers that determine that location in time and space. Even then, that's not a complete description, because you know from Heisenberg's uncertainty principle that an electron can really not be determined in terms of its position and its momentum simultaneously. So this is a roundabout way. We're going to define that location by 4 quantum numbers. These are the 4 quantum numbers. We have n, the principal quantum number. We have what's called the orientation quantum number, that's L. M sub L is the volume or the shape quantum number, and then n sub s is the spin quantum number. So the first quantum number and the fourth quantum number are the easiest quantum numbers to actually determine. The first quantum number, n, is just the row in the periodic table, or the row or the period in the periodic table where the element resides. So if you want to determine the electron configuration of sodium, well, sodium, determine what row sodium resides in the periodic table, and that will be the quantum number, the first quantum number for sodium. Like that, the row where the element resides is going to be your principal quantum number, n. The fourth quantum number is also very easy to determine. The fourth quantum number is your spin quantum number. Either your spin can be plus 1/2 or minus 1/2. So the fourth quantum number has to do with the notion that electrons are actually magnetic. So if you put an element in a magnetic field, those electrons can orient with the magnetic field up, or they can orient down with the magnetic field. So m sub s, your spin quantum number, will either be plus 1/2 or minus 1/2. Now, these second and third quantum numbers are a little bit more tricky. Now, remember, this orientation quantum number, L, actually takes numbers that determine and define the type of orbital that electron resides in. So electrons are going to reside in orbitals, which are energy levels. Some orbitals just are closer to the nucleus. Some orbitals are a little bit far away from the nucleus. So if L is 0, you're dealing with an s orbital, and automatically your m sub L, your shape and distribution quantum number, is going to be 0. This is because the s orbital has only one slot, and that one slot can hold 2 electrons, and those electrons can either be plus 1/2 or minus 1/2, orient against or with the magnetic field, if you were to put a magnetic field on the element. So S having just one slot for those 2 electrons, plus 1/2, minus 1/2, will have an m sub L, the third quantum number, of 0. Now, if your L is 1, that is a p orbital. So 1 is a p orbital, but your m sub L could have 3 different numbers. This is because this p orbital has 3 slots, or we can call them shells, and each shell can hold 2 electrons, as you know. So you can have a situation here where those 2 electrons go into either position -1, or either m sub L position 0, or either position m sub L of 1. An electron can be plus 1 and plus 1/2, minus 1/2, and position -1. It could be plus 1/2 or minus 1/2 in position m sub L 0, or it could be plus 1/2 and minus 1/2 in position m sub L of 1. So there's a total of 6 electrons that the p orbital resides in. Finally, if your L sub is 2, then that's the d orbital. The d orbital has 5 orientations and distributions through space, and so each orbital holds 2 electrons, so that's a total of 10 electrons. The m sub L is going to be either -2, -1, 0, 1, or 2. And again, in each slot here, there's 5 slots for the d orbital. Each slot, the electron will either go plus 1/2 or minus 1/2. The lanthanides and actinides, these are the bottom 2 rows in the periodic table, contain the f orbital. So we're not going to go into tremendous detail of the f orbital, but these have 7 subshells, and there's a total of 14 electrons that the f orbital can house. Again, the lanthanides and actinides are going to have your s orbital. So these f, d, p, and s orbitals actually have a shape. They actually have a volume distribution. And here we're thinking of electrons not only as wave, but also as particles, because these orbitals represent a statistical probability of finding an electron, because there's always an uncertainty in determining an electron in time and position in terms of momentum. So here is what some of these orbitals actually look like. L equals 0 is the s orbital. That's very easy because your m sub L is just going to automatically be 0. And the electrons are always going to fill the s orbital up and down, plus 1/2 and minus 1/2. Your p orbitals have an L of 1, the orientation quantum number, and they have 3 slots. So this slot first gets filled up in the -1, then the 0 slot, and then the 1 slot. That's your ML. So this is a filling known as Hund's rule. And then as they fill up in all the +1/2 states, then they go pair up into the -1/2 states. So that's the order of filling. You may liken this, or an analogy is putting seats or filing seats into a football stadium or a boxing match. The spectators are going to sit closest to the arena or closest to the action. And then when all the good seats are taken, they're going to start to pair up and sit next to one another. Notice here we have shapes of these orbitals. Okay, this is the statistical probability that we will find an electron in time and space. So we can actually determine the location using our 4 quantum numbers. I'll just pick this electron density, this electron here. And let's say that this electron resides in the 1s orbital. It could just as very well reside in the 2s or 3s or 4s orbital. But let's say it resides in the 1s orbital. And let's say we look at this electron here. So what is the address, quote unquote, of this electron? I'm in 1s, so the principal quantum number is 1. S has only one slot, so the L is 0. 0 corresponds with S. And if my L is 0, my M sub L is automatically going to be 0. And this electron is pointing +1/2, or it's pointing up, so that's going to be +1/2. Let's do another example here. This is the p orbital. Let's look at the address, or the 4 quantum numbers that define this electron here. So it's the 2p orbital, so the principal quantum number is 2. That's the easiest quantum number to determine. And then it's an L equals 1. L1 is a p orbital, so if you see a p orbital, think L equals 1. And that's the second quantum number. But what's your third quantum number? Well, what position is this residing in? The p orbital has 3 slots. It's residing in slot 1, and it's pointing down. So it pointing down tells you it's -1/2. The M sub L position 1, which would give you its third quantum number of 1. So this electron has a quote-unquote address of 211 -1/2. Again, the 2 because it's a 2p orbital, energy level 2. A 1 because it's a p orbital. It's a 1 here because it's not in position -1. It's not in position 0. It's in position 1. Okay, these are sort of what we call the subshells where the electron resides. Same thing occurs with d orbitals. This is where if you see a d orbital, your L, your second quantum number is 2, and you fill the electrons like this. Okay, this is Hund's rule, and they all line up straight up, and then they have no place to go, so then they start to pair up. So let's take a look now at the address of this specific electron. So what's the principal quantum number? The principal quantum number is 3 because it's a 3d orbital. And what is L? L is 2. What subshell is this orbital residing in? It's in 0. And what is the spin? Is it pointing up or down? It's pointing up, so it's +1/2. So I would call this 320 +1/2. So those 4 quantum numbers define that position, that quote-unquote address of the electron. So this electron will have a completely different quantum number, set of 4 quantum numbers than this one. And this electron will have a completely different set of 4 quantum numbers than the other one. So every electron is going to have a set of unique 4 quantum numbers that are going to define it. You notice here, as you go up in energy, you're going farther away from the nucleus, and these are just energies that are going to be required on where the electron will reside. So the energy really depends on your principal quantum number and your orientation quantum number. So the 1s is closest to the nucleus, and then your second closest to the nucleus is your 2s, your 2p. These generally are going to be your core electrons. Obviously, as you increase in the atomic number in the periodic table, you're going to go farther away from the nucleus. So once again, your L is going to be 0 for S, your L is going to be 1 for P, and your L is going to be 2 for D, and the M sub L is going to take on these positions, the numbers of these individual subshells. Hund's rule is actually how you're going to place these electrons. So as I stated before, the S electrons, you could just pair them +1/2 and -1/2. These go together as one. For the 1s orbital, the 2s orbital, the 3s orbital, all the s orbitals, the electrons come in up and down. But when you start filling in the p and the d orbitals, you're going to do this one at a time. and then you're going to pair them. So this is how you would want to memorize the order of filling. 1s, then 2s, then 2p, 3s, then 3p, 4s, then after 4s is 3d, 4p, 5s, and then after 5s is 4d, 5p, 6s, and then after 6s you start going to the lanthanides, 4f, 5d, 6p, 7s, and then after 7s you have 5f, 6d, 7p. So if you write this down, 1, 2, 3, 4, 5, 6, 7 down as a column, and then 2, 3, 4, 5, 6, 7 as the second column, and then 3, 4, 5, 6 as your third column, you line up the 1s, the 2s, the 3s, the 4s, the 5s, and the 6s, and the 7s. That will give you the order at which these electrons go. So electrons are a little like soldiers. They're going to go into their slots. So the first electrons are going to go to 1s and then 1s again. Remember, we fill in the 1s orbital. Same thing with the 2s orbital. We fill all of it. And then when we get to 2p, we follow Hund's rule as in the previous slides. We're going to fill in all the subshells and then pair them up. You're going to do that also with the d orbitals and, of course, with the f orbitals. The p has 3 slots. Each slot holds 2 electrons. The d has 5 slots, 5 subshells. Each slot holds 2 electrons. F has 7 subshells or slots, and each slot holds 2 electrons, 1 electron up, 1 electron down. So this is a good way to actually memorize the order and then your energy levels. So the highest energy level is 6s, the lowest energy level is 1s. 1s is closest to the nucleus, 6s is going to be farthest from the nucleus. Now if you can imagine, because the 6s electrons are farther away from the 1s electrons, if you're going to think of ionization energy, the quanta required to eject an electron out of the atom, the electron that's going to come out first are the electrons that are housed in the 6s. Very unlikely that you'll kick out electrons that are housed in the 1s orbital because, one, they're so close to the nucleus. They're the core electrons, and you have to go through all of these electrons before you get to the 1s. Lots of ionization energy, lots of significant quanta of energy to remove electrons from the 1s orbital. The energy is really going to come to eject electrons from these valence electrons. The electron configuration actually has a principal quantum number that's n. So this is your first quantum number. It's the period or the row in which the element you're talking about is. This defines the orbital. So you have to go back to your ordering, 1s, 2s, and then 3s, 3p, the order in which you fill these. And then the superscript is the actual electron in the orbital. So usually electron configurations actually have this type of denotation. So this diagram is actually going to be important because in your lab you're going to be required to fill out this empty periodic table, and you're going to fill it out with all the valence electrons. So use this guide as a way to fill out this periodic table diagram. And you're going to put in just your valence electrons in each of these squares. So that's the first step of the lab, to fill out this periodic table sheet. The way you do that is you're going to look at your periodic table and look at this diagram or comparable diagram. So this would be 1s1, this would be 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, all the way to 2p6 because the p orbital holds 6 electrons. One thing I do want to share with you is that after you go to 4s, it's the 3d electrons that actually get filled. And then after the 3d, it's the 4p electrons. And one final thing I want to tell you is that when you're filling in this sheet, and then you get to the 6s electrons, that's going to be in your 6th row here, 6s electrons. After you fill in 6s electrons, 6s1, 6s2, you're going to go down to the 4f. So this one is going to be 6s2, 4f1, 6s2, 4f2, 6s2, 4f3, 6s2, 4f4, and on and on and on and on we go. So follow the order in which these electrons, like little soldiers, are going to go to their slot. And then you'll have success in filling out that diagram, that chart in your lab. In closing, let's take a look at 2 electron configurations that are sort of anomalous, chromium and silver. So chromium has an atomic number of 24, so we have 24 electrons to fill. It's worth noting that you don't see ions here. You don't see a Cr plus, or you don't see a Cr plus 2. So whatever element that's in the periodic table, if there is no charge, if you don't see an ion, then whatever amount of protons, the atomic number there is, it will also be the number of electrons. So electron configuration is housing all these electrons in their corresponding orbitals. So you just look at the periodic table and that will tell you the number of electrons. Unless, this is the key point here, unless you're talking about ions. The electron configuration of sodium, which is 3s1, is different than the electron configuration of sodium ion, Na+, which has ejected that electron. So it's no longer 3s1, but it's attained an electron configuration of its nearest noble gas. So if you see a plus charge or a minus charge, if you see any ion, then its electron configuration is going to be different because you're removing or gaining electrons. However, if you're looking at something straight from the periodic table that is completely neutral and there is no charge, there is no ion, then the atomic number is going to be the same as the number of electrons. So in that case, chromium as a transition metal has an atomic number of 24. It also means it has 24 electrons. So our goal is to put 24 electrons in this energy diagram. The first electron is going to go here, that's 1s1, and then 1s2. Remember, we fill out the s orbitals first, and then in the p orbitals we follow Hund's rule. So we filled out half of the p orbitals, in this case the 2p, and then we're going to go fill out the rest. And now we go to the 3s orbital. We fill the s orbitals plus 1/2 minus 1/2. P's, we're going to follow Hund's rule. We have to do this until we account for all 24 electrons. All right, so now we are almost at the state here where we are going to have this electron, and we're almost at 24. In fact, that is the 24th electron. So you can count these electrons here, and you should be able to get 24. And this is the electron configuration so far of chromium. It's going to be 1s2, so that's a mistake. That should be 1s2, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. So is the electron configuration 4s2, 3d4, realizing that argon is the electron configuration from here, from 1s2 all the way to 3p6. And that's not correct. So chromium, along with silver, are actually exceptions to the rule. And what happens is that it turns out it's more stable if this electron gets promoted and you have a completely half-filled 3D orbital. So having a completely half-filled 3D orbital or 3D shell is much more stable than just having a 3D with an empty slot here. So what happens is that you have promotion. You have promotion of this electron to here. So let's look at it in the right way, and let's account for all our 24 electrons. And the electron actually gets promoted. Formerly it was at the 4s2 slot, and now you have it here. So according to quantum mechanics, this is a much more stable electron configuration arrangement than the previous one. So a half-filled 3D orbital is much more stable than something that has a gap in the slot and a filled 4s. No, we don't want to do that. We'll promote one of the electrons and have an electron sort of all in one place. Their spin, their fourth quantum number are all pointing up, which is fine, but they are away from each other. So an electron is going to, because it's negatively charged, it will want to get away from each other as best as it can, given that it's stuck in its orbital. So this is the best way to get the electrons maximally away from each other, since electrons are negatively charged. So the answer is the electron configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6. You promote one electron to get half filled in the 3D orbital, so it's 4s1, 3d5. Let's look at silver here. So silver is going to be pretty much the same situation. We have 47 electrons to fill up, and we have the 5s1 electron, 5s2, 4d1, 4d2, 4d3, 4d4, 4d5, 46, 47, 48, 49. That turns out to be the 47th electron in silver, neutral silver, no ions, so we're not giving or taking away any electrons. And this would be what its electron configuration theoretically should be. 1s2, okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, everything is filled 5s2, 4d9. So is that the electron configuration? No. All right. So just as the similar situation before, this 5s2 electron is going to promote itself and have a completely filled 4d orbital or 4d shell. So when you have a completely filled 4d shell, that's much more stable than having a 4d shell that has half a gap empty and then a 5s completely filled. Okay, that electron is going to promote itself much more happier with all the 4Ds completely filled. So looking at it in this way, this pair of electrons actually gets promoted and it goes down here. So this is our new electron configuration for silver, 5s1, 4d10.